Today I have the privilege of being with Professor Ward, the eminent physicist behind the invention of isotactic polypropylene. Professor Ward is responsible for a number of different inventions, but the most important one as far as Wilson Benesch is concerned is the one that was responsible for the diaphragm that is used in all Wilson Benesch loudspeakers, which is made from a material known as isotactic polypropylene. This particular material has some very, very unique properties, and as a result of a collaborative development between Leeds University and Wilson Benesch, we were able to realise a completely new material for our loudspeaker drive unit, and we've been using this material ever since in a number of different forms.
So we made these very stiff and strong polyethylene fibres, but the market wasn't all that large.
Mm-hmm.
And when we got the IRC and had to think up something new,
Yes.
I had the idea that rather than look at conventional composite materials where you put glass or carbon into
A matrix. Yes.
I had the idea, why, as we've got a very, very stiff fibre here,
Yes.
why can't we use that
As the matrix.
as the matrix as well, use it as the fibre in the matrix.
Of course.
And so we started off and we made these sort of panels, that sort of thing, out of the polyethylene.
Yes.
And they really didn't have any major commercial application. And that led us down the line of looking at other polymers. And of course it made a perfect fit with the polypropylene fabric, and it made a perfect fit to take these materials and hot compact them and make them into all sorts of parts, of course. Now the reason it's interesting for you is really just that we hadn't appreciated that polypropylene has got what we call an absorption process for acoustics and just around room temperature. So it's a very, very nice situation where you have a uniform absorption of a whole range of frequencies.
Yes. So the damping within the
just
material.
enough, you get nice damping within the material. The increase in stiffness that you get is a slight advantage to you as well.
So not only does the material have damping, it also
throws out some of the resonances which you might get. It throws it out of the range where you might get them, doesn't it? So you need the increase in stiffness is an advantage.
Is this unique to this material, or is this a very unusual phenomenon in materials?
The materials, all these polymers have absorption processes.
Yes.
But polypropylene is one of the very few, I think it's probably the only few, that has a major relaxation process centred on room temperature.
A relaxation process?
Yes, an absorption process.
Is this at the molecular level? Or?
Yes, at the molecular level, yes.
So the molecules are actually moving around when the sound energy is
exactly, and dissipating it, if you like.
Would you describe that as a fluid, or how, when molecules are moving, surely it is a liquid?
They're called viscoelastic, aren't they?
Ah, right.
So they're halfway between a viscous liquid and an elastic solid.
So it's one of those unusual materials which presents itself as a solid, but when it's been subjected to audio frequencies, it's viscoelastic.
That's right. Yes, yes, that's right. It's able to deform. Yes, that's right. So that's it.
Can you explain to me a little bit more about the process? When I use the term isotactic polypropylene, in my ignorance, I'm saying things which I have no idea what I'm saying. What is it I am actually saying when I say isotactic polypropylene?
The thing is, if you take this sort of linear chain here, this is a model of polyethylene basically. So you have a chain here which has got nothing on it except carbon atoms. Right. And that's why when you stretch it out, it becomes very strong. It's as if all the carbon atoms are arranged as if they were in diamond. But in polypropylene, you actually have what we call a side group. You have a methyl group. You have something on the side, and that makes it into a helix. Right. Now the question is, why is it called isotactic? Well, that's because very Nobel Prize winning scientists called NASA discovered catalysts which would make it so that these metal groups always went on in the same way when you went up the chain. And they were called isotactic. It means sort of equal inclination, basically. So they're all arranged in the same way. So that gives the material a regular helix. So it makes it regular. And
so these atoms are attaching themselves to the carbon in a helix?
Yes, they go around in a helix. And that means the whole thing is regular and it can crystallize.
Right.
And that's important because you want crystallinity to give you a high melting point, all these sort of things.
Stiffness.
So, well, yes, and stiffness. But the polypropylene is of intermediate stiffness.
Right.
It's not as stiff as the polyethylene, but it's intermediate.
Right.
But it suits your purposes very well, really.
From the damping perspective.
Yes, it suits your purposes very well.
So these molecules that are attached to the carbon molecules, is it these molecules that move or when it's subjected to the sand, or are all the molecules moving when
all the molecules are moving around, yes.
Right.
It's called it's when it's going from the glass to a rubber, when it's going from an elastic solid to a viscous liquid, if you like. It's
Right.
not there yet, but
Right.
it's doing that. And that's why it's called, it's a viscoelastic relaxation process.
Is this what I've read somewhere where basically it's moving from a glass phase to a rubber transition phase?
Yes, it's called a glass rubber transition, yes.
Right.
TG, yes. And it just so happens that it's around room temperature for polypropylene. It suits your purposes.
Interesting.
But it doesn't melt, of course,
No.
until you get up to 130, whatever, 190, whatever.
Right.
So you've got a high temperature melting point.
What role is the carbon playing in this structure? Is it is it the carbon where the strength comes from, or is it the structure of the geometry of the molecular structure that gives it the strength?
No, the strength comes from the chain, yes.
From the helix chain?
Yes, from the helix from the chain, yes. It's like pulling on a spring. It's just like pulling on a spring.
Right.
So, and you can model it like that. So it would just be like, it's just like a coiled spring.
Uh-huh.
And the stiffness is very close. In these highly oriented materials, it's perhaps a third of the stiffness you'd get if it was perfect.
Right.
But you're just pulling on it, really.
So once this has actually been formed and we've created a sheet material, obviously then we've got to develop a process whereby we actually shape this material into useful objects.
And that's again where polypropylene is rather useful, because you can go up to the temperatures below the melting point where it becomes pliable, but it still hasn't melted. So there's enough mobility in it, in the structure, to allow you to form it.
And this is still a woven, regarded as a woven structure, isn't it?
Oh, yes.
So when you're talking about hot compaction, you're literally talking about the outer skin of the material being melted, as it were. Is that right?
What happens here, yes, is that if you take a sheet like this, close to its melting point, then the trick is that the surface of each of these individual elements has a slightly lower melting point than the bulk interior. So you, believe it or not, you can melt a thin skin on the surface of every element here, quite uniformly. So you then cool it down, and that freezes and forms the matrix.
Right.
So you start off with a whole lot of fibres that are not connected in any way. You heat it up just below its melting point, a skin forms, which melts. You cool it down, and that freezes, and then you've got the whole of this with a matrix of that skin, which is
fantastic.
And that's the trick. And I think it wasn't really appreciated that this would happen. I think the sort of, if you were just sort of commonsensical, you'd say, well, if I take something like this and I put it in a heated press, it'll start melting from the outside.
Yes.
But that's, if you do it carefully, then you can get each individual element.
So if you were looking at the fibre and it was a circle,
yes,
the whole of the outer perimeter
it's like a ring.
Melt.
You have a ring.
A ring of molten
That's
material.
right. And then, of course, if you do it under a certain amount of pressure, that spreads out, fills all the gaps, So you have a perfect 100%
Fibrous structure.
fibrous structure, which is reinforced with the same polymer.
So would the energy that is being absorbed in each one of these fibres, it would actually be absorbed in a straight line according to the direction of the fibre? Is that, or would it, or does it?
No, there is an element. Yes, it would. Yes, it does depend on, but that, you know, you've got an average here. It's because these things are like sending a tennis ball into a tennis racket. You see what I mean?
Right.
You know,
it
tennis
dissipates
racket.
the energy by transferring all the energy.
You have to take all the bits up. You see.
Right.
So if you hit this, it has tremendous damage tolerance.
Right.
You can imagine that.
Of course.
Just like, you know, the analogy is with the tennis racket, hitting a ball with a tennis racket.
I would imagine also that by virtue of the fibres being orientated when it's being shaped, they will actually tend to flow into the main stress lines also.
Yes. It's
providing stiffness where it needs to be in a way that is very organic rather than...
Yes, yes, there are a lot of things that are on our side in these things, which are rather surprising in a way, and you're absolutely right about that.
By virtue of the fact that it's a woven structure and, it's got the lines moving in the direction.
Well, it has continuity within it, doesn't it?
Yeah.
It's not as if you're putting, you know, bits of glass fibre into something where they might or might not follow the follow the contours.
You can actually see that in the cone because you can see how the fibres
they're forced to follow the deformation that you put in, aren't they?
Yes.
So as I say, I think the analogy is if you imagined you could take a tennis racket and you could freeze it when you'd done that.
Yes.
Then that would be exactly the analogy.
Yes.
Because all the strings would be pointing in all the directions you wanted.
Exactly the right direction that they need to be.
Yes, exactly.
Perfectly aligned.
Yes, perfectly aligned. So
I think we can see that here also in this.
Yes.
The lines here actually give a very good illustration of what Professor was referring to with regard to the lines are following exactly where the stress lines would be if you were to finite element and analyse this. They would be exactly the same.
Well, that's right, and in fact the group at Nottingham University in engineering we worked with, Professor Long and his colleagues, have done exactly this sort of thing in collaboration with us just to show how this works. And you're absolutely right about that. It's it can be modelled by finite element analysis, and it follows the deformation pattern. No, it's but that's something we discovered, isn't it? I mean, if we hadn't met at this meeting,
the smart
where we got, well, that was for another of our inventions, for our lithium battery inventions.
Oh right, so
that's a totally different invention. Yes.
So you were there for a totally different reason from the materials that we were actually.
Yes, that's right. That was for making rechargeable lithium batteries, and in fact we just had lunch together, didn't we?
That's right.
And we started talking, and we thought, you know, we knew we could make a shape for you, but of course we didn't know then that it would have everything you wanted, really.